Hello, here's a simple harmonic motion question. We've got a particle, I've got no diagram this time, so we're going to have to actually draw one. We've got a particle moving with SHM on a line between 2 points A and B. So A and B, these are 0.4 meters apart. So that's 0.4 meters. So we've got an amplitude of 0.2. So let's write that down already. That's our amplitude, 0.2 meters. Maximum speed of the particle is 0.8 meters per second. V max equals 0.8 meters per second. We might as well put in straight away that we know that is omega A from our knowledge of SHM. The particle passes through a point C, 0.1 meters from A. That's that C, and this is 0.1 meters. Okay, so that's everything there. Find the period of the motion. Well, we've already got that dropping out of here because we know that omega is equal to 2 pi over t. And we've got that omega is equal to 0.8 divided by 0.2, which is 4. So that's going to make t equal to pi over 2 seconds. So that was easy enough. Find the speed of the particle when it's at C. Yeah, okay, so with these, you'll have some people who jump straight to the formula booklet and they'll find there, the v squared equals, what is it, omega squared, a squared minus x squared, which is fine, I suppose, but let's go for just a slightly more involved approach then. Let's start the motion, say the motion started at the origin. We want to get the speed when it's at C. So we could say that the displacement is A sine omega t. So that's where we're starting at 0 here. We've got no phase shift going on. We just got the simple definition of displacement. We know that the velocity is A omega cos omega t. In that case, that's why we've got this V max over here being omega A, or A omega as I've written it in that formula. So we can plug in a whole load of stuff here and work out, from our displacement equation, we've got 0.1, because that would be our displacement when we've got to C, is going to be equal to, it doesn't really matter if we've done this positive or negatively, the minus sign doesn't matter. The speed at C would be the same as the speed on another side if we had D over here at 0.1 meters. So I'm not going to worry about the minus sign there, but that's our displacement. Our amplitude we know is 0.2, and then we've got sine of 4t, because we've already worked out what omega is. So sine of 4t is going to have to be a half. So t is going to have to be pi by 6. 4t is going to have to be pi by 6. So we've got that t is pi by 24. That is going to be a time that we've passed through the point C or D, whichever one we're looking at. It doesn't really matter which one we're going for. Now we can stick that into our velocity equation. So the velocity at that point is going to be equal to 0.2 multiplied by 4 multiplied by cos of 4 lots of t, so pi by 6. So that's a root 3 over 2. So we've got 0.4 times root 3, which is 2/5 of root 3. And that is our meters per second. Of course, if we just stuck this straight into the equation at the top, if we put that in there, we would have had omega squared, which is 16. Then we've got to multiply by various horrible numbers that are coming out of this. So we've got a, what was A again? 0.2, so 0.04 minus 0.01, and you can see where the square root of 3 is now coming into all of this. We can take that factor outside, so we've got a factor of 100 there, haven't we? So we'd have so we've got 4 over 10 by the time we square root it, because we've got 16 over 100, so square root it, 4 over 10, 2/5 of root 3. So it comes out exactly the same thing, which again isn't really surprising. because, well, that's what we want these equations to do. But yeah, this is it's got all of this working out built into it. That's where it's come from. But it's not really that much longer to go back to these first principles here of what the definition is of simple harmonic motion and how we're going through our trig calculus on it all. So yeah, two different ways of getting the same answer there. Given that the particle is at rest at A at time t equals 0, find an expression from the displacement of the particle from A. Okay, right. So, well, let's start by getting, well, we've got our expression here, which is displacement from O, from the center. So we'll start off, and I'll leave a bit of space on this so we can manipulate things. So we know we've got to have somewhere in all of this a 0.2. Well, we have to decide. I mean, I've decided here with a sign, but we've got to decide whether we've got a sine or a cosine going on in this. And then we know we're going to have a 4t at the end. So we have to have various bits going on there. Right, so are we going to want, if we're starting at A rather than O, we don't want to have the 0, we don't want sine in there because that keeps us at the equilibrium point, whereas cosine gets us at the amplitudes. So we're going to want a cos in there. So we've got a 0.2 cos 4t, because that's going to put us at an amplitude. If we want to get at A, well, A is in the negative direction in this case, so let's put a minus 0.2, because we're measuring that way to be negative. So we've got a minus 0.2 cos 4t. That's just describing things relative to O, but at least it started us at an amplitude. Now we want to get this displacement relative to A, not to O. So we need to do a shift in a translation in the x direction, and we're moving in the negative direction. So if we're going to translate in the negative direction, we need to add it on. So we're going to do a 0.2. We add on 0.2 to all of that, and that starts us as A. So doing a quick sanity check on this, at least for time t equals 0, the displacement will be 0.2 minus 0.2. So yeah, we've got 0 displacement from A at that point. And then yeah, once we've got out to the other side, we're going to get a maximum of 0.4, which is what we expect. So yeah, that's looking fairly sane. But I suppose the two key things on this are deciding whether to use sine or cosine, which is really, are you starting at the equilibrium point or are you starting at the amplitude? Unless you've got a phase shift in it, in which case, you know, you can just fiddle stuff around as you see fit to start it at some other point in the cycle. Decide on this minus sign, and that's just purely on which direction you're taking to be positive or negative, and then do the shift to one of the amplitudes. So if we were going to be doing, you know, starting at B, well, we're just taking the negative of both of these terms, and then we'll be starting on the other side, because this would be in the positive direction, so we'd make that a plus, and then this would be a shift in the positive direction, which means we'd make that a minus. So yeah, it's quite easy to move from one point to another in the cycle, in the oscillation. Right, so find the time that it takes for the particle to move from A to C. Okay, so we need to solve this really in order to get the time. So we're saying that S is going to be 0.1, and that is going to be equal to 0.2 minus 0.2 cos 4t. So we just need to put all of that together. So we've got a 0.1 divided by a 0.2. So cos of 4t is equal to a half. So 4t is going to be equal to pi by 3. So t will be equal to pi divided by 12 seconds. So that's just solving a fairly simple trig equation. But yeah, this is a nice question, this. So it's more of a mathematically driven question, I suppose, rather than a physics question. There's no context put on it, but it covers a lot of the key ground. You know, we're pulling out quickly, getting periods and speeds in the motion just based on these values they're giving us. You know, the amplitude and things like that. it's very quick to work these things out then. Once they've given us a speed, a maximum speed and an amplitude, everything's just dropping out from these trig equations. So yeah, this is covering a lot of the basics of SHM.